So this is examples class 7, using sampling distributions and the central limit theorem. We'll be looking at confidence intervals for the population mean and proportion. So example 1 is making use of the normal distribution. We have a problem on IQ test scores. We're told here that membership in Mensa requires an IQ score of 131.5 or higher. We're given that 9 candidates take IQ tests and their average IQ score was 133. Now, in this problem, we're allowed to make the assumption that IQ scores in the general population are normally distributed with a mean of 100 and a standard deviation of 15. This means that we know the standard deviation for the population. And this means that we can use a normal distribution. So for part A, here, part A, we're asked to find the probability for a single person, one person selected at random. We've done this kind of thing before, has a probability of more than 133. So we're looking in part A at the value x, the probability that x is bigger than 133, where x is a value, a person from the normal population of IQ with 100 as the mean and 15 as the standard deviation. So the probability that x is bigger than 133, we generally write that down. It's a right-hand side top end probability, so we write it as 1 minus the probability that x is less than 133. And of course for that we can use the norm dist function in Excel, as we've done many times before. 1 minus norm dist, we're putting in 133 for the x value, 100 for the mean, 15 for the standard deviation, and 1 for cumulative, and that will give us a probability of 0.0139. So that's the probability that a randomly chosen person from the population has an IQ score of more than 133. So in part B, we're looking at the probability that if we choose 9 people at random, that the probability that their average IQ score is bigger than 133, at least 133. So here we're looking for the probability that x bar is bigger than 133, where we know that now this is x bar, so it's the sampling distribution of the mean, and this means that x bar comes from a normal distribution which has a same mean value, 100, but the standard deviation this time is the standard error, which is the standard deviation divided by the square root of sample size. So standard deviation, square root of sample size, sigma over the square root of n. So here we've got 15 divided by the square root of 9. The sample had 9 people in it, and we have 15 divided by 3, which of course is 5. So we have x bar coming from a normal distribution with a mean of 100 and a standard deviation, because it's the standard error, of 5. So the probability that x bar is bigger than 133, again we can write that down by saying 1 minus the probability that x bar is less than 133. And that means we can write 1 minus norm dist, again using exactly the same Excel function, but this time we have 133 for x, we have 100 for the mean, but we have 5 for the standard deviation, and the cumulative value 1 again, so we have exactly the same kind of form, and this gives us 2.06 times 10 to the minus 11, a really, really small value, equals 0 to 4 decimal places, 0.0000 to 4 decimal places. Practically 0. So it's very unlikely that we would have the probability of the sample mean of those 9 people being bigger than 133. Now, part C of that question said if their individual scores, okay, 9 candidates, their individual test scores were lost, can it be concluded that all 9 candidates have IQ scores above 131.5? Well, in fact, no, that's not necessarily true. What we can say here is the average x bar could be bigger than 133, but individual values could still be smaller than 131.5. The average can be bigger than 133, whilst an individual value could be smaller than 131.5, because this is about the average of that sample. An individual value can still be much smaller, even though the average is 133, because there could be much higher values compensating for that. So the average can be bigger than 133, but an individual person's score could be below 131.5.